I put up the recording pretty late last night. If my computer goes to sleep, it stops converting the file, unfortunately. So I didn't realize that again until quite late last night. So I got the video up. I also posted the homework solutions up through the ones that you were working on. So I'll try to put those up after class. All right. So we finished the volumes of revolution using disk and washer method yesterday. So we can go ahead and work on cylindrical shells method today. And typically they do follow the pattern that if you go about the x-axis, it's typically easier to do the disk or washer method. And if you go about the y-axis, it is typically easier to use cylindrical shells. That doesn't mean that you can only do it that way, right? If you go about the other axis, you just have to change the variable that you integrate with respect to. So just like above, we add up our Riemann sum. And the question is, how do we get this sum this time? So we're using cylindrical shells, right? So a cylinder that is very thin, right? It's almost like a piece of paper rolled up into a cylinder is basically what we're using here. And if I were to slice that cylinder and unravel it, it would roll back out into a piece of paper, basically. And what are the dimensions of that paper? Well, whatever this height is here would be this distance, this height. And this length would be equal to the circumference of that circle. So that's 2 pi r. So if I wanted to add up the area for cylinders, I'd have 2 pi r h, and then there's this delta x, which is the thickness of the piece of paper. So notice x is r and f of x is h. So let me just draw on this paper here, or this screen here. Let's say we're using this cylindrical shell right here. The distance from the axis out to the slice of that shell is x or r in this case. And that should make sense. That is the radius of the cylinder. But we call that distance from the axis to the slice x. And then the distance from the x-axis up to the slice is the height, f of x. Now the slice is technically this. Because then we have to wrap that all the way around. So radius is x, height is f of x. Therefore, the volume is 2 pi times the integral of x times f of x dx. But what I want you to really remember is this is radius, this is height. Because those two things can change, right? It's not always going to be x, it's not always going to be just f of x. So let's go ahead and try one of these. It says the area bounded by this function, e to the x squared. It also says and x equal y equals 0. That is typically going to tell us that we're in the first quadrant. And they give us our bounds. And then they also tell us to rotate about the y-axis. So what does e to the x squared look like? Well, it looks like your typical exponential, but it's going to go up a little faster. And if we're going from 0 to log 3, so right, this equation would typically go back here, but we're starting at 0, so we don't want any of that. And we're going out to, let's say right here is where log 3 is. Okay, so that is the function that I want to wrap around the axis. So if I do that, and it comes over here, something like that. Now again, you have to realize that this thing wraps all the way around. So the way I would picture this is maybe like it's kind of like a bowl, right? It's got the cutout of a bowl in the center, but instead of it being rounded on the outside, it is maybe rectangular on the outside, or maybe even square. Or, well, it's still rounded, but it's got a flat edge rather than curved. Let's put it that way. So maybe if we looked at it from above, it would still look like this. Okay. So again, I want to take a slice, do the same thing on the other side. And if I connect it, I should see that it looks like a cylindrical shell. And we know that the volume for a shell is 2 pi integral. They told us to go from 0 to natural log 3. The distance between the axis and the slice is x. It's our radius. And our height is whatever the height of the function is there. Our function was e to the x squared. And then our thickness is dx. So now we just have to solve this integral. Looks like if we let u equal x squared, du is going to be 2x dx. One thing I can do is I can steal this 2 from out here. And pull it back inside. And if you really want, we can write it next to the dx. So this is e to the u, and that's du. And while we're at it, let's go ahead and change our bounds. So if x equals 0, 0 squared is still 0. So that's the same bound on u. And if x is natural log 3, u is natural log 3 quantity squared. Now this is a great integral, right? Integral e to the u is just e to the u. And just simplifying, should be that. So any questions about that guy?
Sorry, I think I just got lost when we changed the bounds. Would it be e to the natural log 3 squared because it's x squared in the exponent, or
E squared. So log 3 is the x bound, right?
mm-hmm.
So you would substitute it in here.
Okay.
So log of 3 squared would be the new value for u.
So if you change the bounds before you do it, then do you not have to resubstitute in for u?
I did substitute for u, but I don't have to plug in the x values again.
Okay, that makes sense. Thank you.
Yeah, these bounds are now bounds on u, so I don't have to back substitute.
That makes sense. Thank you.
Mm-hmm. Dan, did you have something? I see you're unmuted there.
Okay. For with the back substitution, like say if you were not to replace, or if you replace the u of x, wouldn't it just be ln 3 over 0 for the bounds?
Yeah, if you plugged u back in of x squared at this point, then your bounds would be 0 and log 3.
Okay. Just checking.
The thing I was most worried about is I thought you guys would try to simplify this, because it's e to the log, but it's log of something all squared, so you can't cancel them. I'm trying to think what would be best for me to do here in terms of the problems. I think I might go ahead and give you this one and one of these. I'll let you do that one. Because I think the more practice that you have, the better off you'll be. So let me go ahead and do C part 2. All right. So x minus x cubed. So off the top of my head, I don't know what that looks like, so I'm going to plot it quickly. What are the bounds here on the problem? They don't tell us. It says x equal y equals 0. So let's start at x equals 0, and I don't know, go to 5. Okay. Okay, so this one was always an interesting one, because if you don't zoom in, then you don't see exactly what you're supposed to do. So I only went out to 5 here, right? But there's actually a part of this curve that goes above the axis back here. If I zoom back in to say 2, now I can see it. So this curve goes above and then crosses at 1. Now, because it told me I have to be, or I'm bounded by x equals 0 and y equals 0, well, the line y equals 0 is the x-axis. So if I go below that, then I don't use any of that function. So it appears it's 1. Of course, when the scale changes, right, notice the x-axis scale is 0.2 and the same distance on the y scale is 0.1. That's why it's so exaggerated. But I can zoom in and I can see clearly that this goes above the axis. So if I come back here now and just do a quick sketch of this guy. So it went like that. And it tells me to rotate about x equals 3. So this point from the graph looked like 1, 2. So I'm rotating about this point. 4. So something like that. Again, I need to take a little slice. Same thing over here. Forgive my drawing skills. Okay, so that's half of a cylindrical shell. Now, my volume is always 2 pi integral. My bounds, I need to find out when does x minus x cubed cross the axis, right? So that point and that point. And that's pretty simple. I can factor out an x here. That tells me x equals 0 is one of them. This one's going to tell me that x is plus and minus 1, right? Well, clearly I only need plus 1. So I go 0 to 1 for my bounds. Now I've got to define my radius and my height. The height's easy. It's just the function. Okay, so that's the height. Now the question is, what is my radius? Well, we define this distance as x, but my radius is from my axis of rotation out to the slice. This distance here we know to be 3. So how would you define r?
Three minus x.
Right. So if they choose some axis besides the y-axis, then that affects the radius. So we're all done with the setup. Now we actually have to solve this thing. So I'm going to go ahead and multiply this all out. I'm going to get 3x minus 3x cubed minus x squared plus x to the fourth. So that's going to be 3x squared over 2, 3x to the fourth over 4, x cubed over 3, x to the fifth over 5. Right, all very simple integrals. And even better, we have just 1 that we have to plug in here, and 0. Again, I don't have enough room there, so forgive me for going down to the next line here. Okay. And as I said, the beauty here is all these are 0. And every one of these powers 1 just as 1. So we end up with 2 pi. And we've got 3 halves minus 3 fourths minus 1/3 plus 1/5. It all comes out as 2 pi times, it's like 37 over 60. Or 37 pi over 30. So any questions about that one?
Yes, I have a question. So we have the bounds as 1 to 0. Is that because when we did the graph, like when you graphed it, so because it's the x equals y equals 0, and then when we graphed it, we saw it went to the 1?
So it says bounded by the function, and we can't go any further than x equals 0, which means we're bound on this side, right? And we can't be any lower than y equals 0, which means we're bounded above. So that stops us here and there, and then I just solve for those 2 points.
Okay.
I guess a better way to, if they would write this, would be greater than.
Yeah, that makes sense. And you said, so basically the x equals plus or minus 1 means that it can't be the negative 1 because we're bounded in the first quadrant?
Yeah.
Okay.
Yeah, if I were to come back here and plot the function over a different range, right, you see that it is in fact touching at 1 and -1. But because the problem tells us we're bounded within the first quadrant, we don't need any of this information over here.
Okay, so I don't know if it's gonna apply ever, but like, how would it be written if it was something that was bounded only in like quadrant 2 or quadrant 3? Like, because how you were saying, like, it would make more sense to be like, it has to be like greater than or equal to 0 for the bounds. But like, how would they write the bounds if it was all going to be, you know, negatives, or x is, you know, negative and y was positive?
I'd have to look that up. There's not many examples I've seen where they've done that.
Okay.
which
We
is
don't really
probably-
have to worry about it though, then.
I don't think so. I don't think I would surprise you with something like that.
Okay. Okay, cool.
I don't generally like to surprise anybody.
Okay, awesome.
So are we okay with this one?
Yep.
Okay. So I'm going to go ahead and leave the other two for you guys to go ahead and try for a few minutes. So you've got B here. If you want to hurry up and jot that down. And then I would also like you to do the same problem we just did, but instead of about the line x equal 3, just do it about the y-axis. So you might want to start with that one. I think that'd probably be the simpler of the two. And I'm going to share with you the arc length and surface area sheet. So we've done all those integrals. We're trying to put them to good use with some applications. And we started with volumes of revolution. So we did both disk and washer method and cylindrical shells. And just as a quick aside, if you're curious where that sort of stuff is used, besides the few examples I gave you at the very beginning, or at least in my field in physics, often you have to solve triple integrals. And those integrals are dealing with the shape of, say, a charge distribution. So you might be talking about something like as simple as, you guys know what a coaxial cable is? Right, the cable that plugs in your internet, not an Ethernet, but the coaxial cable that might come from, the cable company. It's got the one little prong inside. Okay, so
There's
that's a coaxial. What's that?
modem, technically.
Yeah, true. So that cable, it's got a single wire running through the center, and then it's got the outer casing, which is also some kind of conductor. And those two things can have charges on them. And if you like, you can calculate the electric field, the electric potential, both between the wire and the outer cladding, or you could calculate it outside the wire completely and see how much, electric field's getting through the wire, that sort of thing. All of those require integrating about a surface. And so you have to rotate all the way around. But the nice thing is you typically have symmetry. So you're looking at spheres, cylinders, things like that. So anyhow, that's just a quick application of using this rotational axis and creating some kind of shape. All right, so the next thing that we want to try to do is look at arc length. So arc length is something that's not new. We've done this before, and we've done this as the distance formula. So we can calculate the distance between 2 points using the distance formula. And if you don't remember it, it's given to you right here on the page. It's x2 minus x1 squared plus y2 minus y1 squared. Notice that they then change that to delta x and delta y, right? We recognize that as a change in x and change in y, as opposed to x2 minus x1 and so on. And I'm going to manipulate this equation and change it into what we would expect to see in calculus so we can make it into an integral. And the reason we want to make it an integral is because notice in this picture up here, we can take points along this curve and we can draw a bunch of little straight lines between them. And if we add up all of these line segments, we can get a pretty good approximation to the length of the curve. And so in order to do a sum, right, we integrate. So let's start with this formula right here, the distance formula. And it says factor out delta x squared. So I'm going to take that square root. I'm going to factor out delta x squared. So delta x squared from delta x squared, that's just 1. And if I try to take it away from delta y squared, well, then that's really rewriting it this way. And if that seems a little strange to you, then go ahead and multiply the delta x squared back in, and clearly you'll see you'll be left with just delta y squared for your second term there. So why in the world did I do that? Well, delta x in calculus translates to dx. And if I'm talking about integrating, I got to have a dx or dy or some kind of differential, right? So the square root of delta x squared is delta x. So this is delta x square root 1 plus. Now I've got delta y quantity squared over delta x quantity squared. If they're both squared, why can't I write them as one thing all to the second power? Like so. Now, we just got done saying delta x translates directly to dx. What do you think delta y over delta x is going to be?
Would it be dy over dx?
Right? Or delta y over delta x, isn't that a slope? And then we represent slope in calculus with a derivative, right? So delta x becomes dx, and delta y over delta x is dy dx. So then if we can also rewrite dy dx, if you really want to, as f prime. And we introduce an integral. All right. From some a to b, well, we've got the square root of 1 plus f prime quantity squared dx. So that's how we get our formula for the arc length. And you're going to like this, I think, because arc length, all you need to do is take a derivative, plug it in, and integrate. There's really no whole lot of guesswork here. So let's try this first one. It says graph and compute the length of the curve. We're given that f of x equals 2x minus 3, and it's the length from 2 to 4. So we know that's a line, right? 2x minus 3. So it's almost silly in terms of needing an integral to solve this. We could simply plug in x equal 2 and x equal 4 and find the corresponding y values and use the distance formula. But let's go ahead and, we're trying to learn how to use this technique. So let's start off with a simple example. So I have f. I need f prime. That's real tough. That's 2. My arc length formula is integral from 2 to 4 in this case, square root 1 plus, I need f prime, which is 2, squared dx. Well, that's easy. Square root of 1 plus 2 squared, that's square root of 5. And square root of 5 is a constant, so I can pull it out in front. So then I just have integral of dx. That's easy. That's just x. From 2 to 4. And just plug in. We end up with 2 root of 5. So let me just look at the other examples I have here. Try to figure out which one I need to do for you. Remember, this one gets kind of ugly, so I'll probably do that one for you. I think maybe I'll leave this one for you to do. So let's go ahead and take a look at B. We're given the function, and we're given from 0 to 2. So we know right away that the integral is from 0 to 2. Square root 1 plus. Now I need to find f prime. So this is 2 times, now we have x to the 3 halves. The derivative of that says bring the 3 halves down in front and subtract 1 from that power. So it becomes 1/2. And those 2's cancel. So this is really 3 square root of x. So we plug in 3 square root of x, and we have to square it in the formula. So 3 squared of x squared is 9x. How would I solve this integral?
Could you let u equal 1 plus 9x?
So it is just a u substitution. I let u equal 1 plus 9x. du is 9 dx, which means I need to put a 9 in here and a 1/9 out front. And then this is the square root of u, or u to the 1/2 power du. You guys seem to not like when I change the bounds, so I'm going to leave it. Integrate u to the 1/2, you get 2/3 u to the 3/2. I'm just putting a to b here for placeholders. And then u is equal to 1 plus 9x to the 3/2, evaluated from 0 to 2. So plug in. And unfortunately, that's as good as we're going to get for a solution. Good with that?
Yeah.
Okay. So let me go ahead and do this last one for you, and then I will go ahead and introduce the other topic. And then the rest of class I'll leave for you guys to go ahead and try the problems. So again, let's start off with f prime. So we get that, right? And off the top of my head, I can't remember if I want to put these together or not. I'm not sure what's the best method. So let's go ahead and do that to see what it looks like. Okay. And I could factor the top, but it's not going to be the same factor, so it's probably not the best choice, but let's see. So arc length, integral, we have our bounds given to us, 1 to e, square root, 1 plus f prime It's quantity squared. So I'm just trying to think which form do I want to plug in. I think I will go ahead and plug in the x squared minus 4 over 4x. And that has to be squared. And of course, we need dx. Everybody with me so far? Why did that move? Okay. Now we got to do a bunch of algebra. So I've got, now instead of 1, I know that I've got this 4x squared down here. So if I want to put these things together, then I want to write this as 4x over 4x squared. Let's see if that helps us out. So you're probably sitting there going, you're crazy. Why did you do that? Well, I did that because I want to get rid of the fraction altogether. So if I rewrite 1 as the same thing as the denominator here into that power, then I can make this integral look like this. Which means the square root of a quantity squared can get pulled out. So I can take out that 4x squared. And it just becomes a 4x outside. And then on the inside, I've got 16x squared. Then I'm going to get x to the 4th minus 8x squared plus 16. Right, all I did was square out both terms. And this is going to then be x to the 4th plus 8x squared plus 16. So can we get two numbers that multiply to 16 and add to 8?
Four and 4.
So it looks like that'll work for us.
Yeah.
Right, the square root and the square would cancel there. So right now it looks like I've got 1/4 integral x squared plus 4 over x dx. And I think the best way to treat that would be to just break it into two separate integrals. So x squared over x just becomes the integral of x dx. And we should know that that's x squared over 2 when integrated. And the second one is the integral of dx over x, which hopefully you recognize as natural log. And then I'm just going to plug in. Natural log of 1 is 0, so that's great. Natural log of e is 1. So after much manipulation, arithmetic, and algebra, it appears we come out with e squared plus 7 all over 8. Questions? Thoughts? Concerns? All right. I'm assuming you just got to let that sink in. So what I would like to do is go ahead and introduce you to surface area, which you might be thinking, oh no, another topic. But it's only one thing different than the previous. Notice the formula. We got the square root of 1 plus f prime squared dx in there. We're just now introducing a 2 pi f of x out in front. So why are we doing that? Well, if we're looking for the surface area, right, that means we're taking a curve, we're rotating it about the axis, and we're looking for the outer shell, right, the area of the outer shell. Well, what does this shape kind of look like to you? Something that we just recently did today.
The cylindrical shell.
It looks a lot like a cylindrical shell. It just looks a little off because it looks like the radii is changing, right? So notice in this equation, we've got 2 pi f of x. That's in the place that we would normally put radius. And that's because the height of the function is the radius, right? And that changes depending on where you are. And when we did cylindrical shells, this distance was considered rather thin, right? Well, in this case, we're doing that the thickness of the shell is still thin. That's dx. And now this length is the height of our cylinder. And we just got done talking about the height, or that length there, as being the arc length, right? 1 plus f prime squared. So that's where all of this equation comes from. It's as though we're using cylindrical shells basically again. And as I said, we got our arc length in here. That's our radius. And then, of course, we need our 2 pi. So again, there is an equation that we can use. It's not a whole lot different than the last one. So let's go ahead and try one. Let me see how many there are of these. There's 3 of these. Okay. Which one do I want to do? Maybe I'll try this one, see how it goes. So as always, we need f prime. Let's start there. So this is 2 square root of x, which means when I take my derivative, I'm going to bring that 1/2 down and subtract 1 from the power, which makes it minus 1/2. And simplifying, this will be 1 over square root of x. So now let me use my formula. And again, I think I accidentally wrote volume up here, didn't I? No, L, okay. So L is for the arc length. For some reason, they also use it for surface area, which is absolutely silly. I'm going to call this S sub A for surface area. So S sub A is 2 pi integral f of x square root 1 plus f prime squared dx. So for this problem, we have 2 pi integral. They tell us from 1 to 3, so it's integrating from 1 to 3. F of x is 2 square root of x. Then we have square root of 1 plus f prime, which is 1 over square root x squared dx. So this is 4 pi square root x. And I have square root. This is going to be 1 plus 1 over x. Right, because square root squared just returns what's inside. Now, in the past, I feel like this has been a sticking point for a lot of students. When you see this, what thoughts do you have to continue?
I mean, one thing I see you might be able to do is, would you be able to cancel the x within within the 1 over x? So like say if you multiply them, when the x cancel, well actually no, you want that.
Anybody else want to share? I think you're on the right track.
So could you just under the square root do x times 1 plus 1 over x?
So because they're 2 square roots, we can put them together, right? As a single radical. So I'm not sure why, but that's like a lot of people's first instinct is not to do that. They want to try to integrate right here. And it's not the best choice. Because these are both square roots, right? The square root of a times the square root of b is just square root of a times b. So if we put these two things together, and then multiply or distribute that x, this is going to be x plus 1. dx. Now we can go ahead and work on solving the integral. We can let u equal x plus 1. Du is dx. And in this case, I am going to go ahead and change my bounds. So when x is 1, u is 2. Right, I'm just plugging them in there. And when x is 3, u is 4. So integral of u to the 1/2 is 2/3 u to the 3/2. And now it's just a matter of plugging in and simplifying. So square root of 4 is 2. 2 cubed is 8. And then 2 to the 3/2, well, 2 cubed is 8, and the square root of that is 2 root 2. So I guess that's probably the nicest way to write it. So this guy is square root of 8. That's how I got that guy. So again, I think the hardest part of these problems realistically is a lot of the arithmetic and substitution. Calculus, not too bad. And the setup isn't too bad because you just got to follow the formula. Would you guys like to try the rest of these problems? Or do you need to see another surface area problem?
Could you do another surface area problem?
Sure, I could do this one here if you like.
Okay, thank you.
So they tell us from 0 to 2, my function is x cubed over 3. Then I need square root 1 plus the derivative of that squared. So what's the derivative of x cubed over 3? It's just x squared, right? Because you bring the 3 down, take 1 from the power. So then x squared squared would be x to the 4th.
Or would you be able to use one of the x squares to cancel out the radical then, or no?
Did you say to cancel the radical?
Yes. Does that not apply?
The only reason you cannot do that is because you have this plus here.
Okay.
If it was this instead, you could.
Okay, gotcha. Thank you.
Don't we need a dx on the end of all the problems?
Hey, you didn't see that? Come on, man. All right, so how will we go about solving this now? I'm gonna go ahead and throw this 1/3 out front here. I think we can just do a U sub again, right? So if we let u equal everything under the radical, du is 4x cubed dx. So we need a 4 out here. And then we need a 1/4 down there or out there. So we got pi over 6 out front. And then inside, all of that is du. And we have u to the 1/2. And again, if u is, or if x is 0, u is 1. If x is 2, u is 17. And it's the same integral as last time, right? 2/3 u to the 3/2. Except this time it's not going to simplify very nicely. Now the one that I left you is going to be related to the arc length problem that I did that had the two fractions. So let me just go back to that one really quickly. So I wanted to point out one thing here. So in this problem, remember I created this fraction and plugged in, but I had originally started with this quantity. So what I wanted to point out was if I start with the x over 4 minus 1 over x, and I had plugged it in, I would have squared it. And then I would have had plus 1 under the radical. So if I were to square this whole thing out and add 1, what happens is I get this. So let's just do that really quick. So 1 plus, this is going to be x squared over 16. Multiplying them together, n times 2, you get minus 1/2. And then squaring 1 over x, get 1 over x squared. So then you have 1 minus 1/2 there. So you'll see that these terms and these terms look exactly the same. The only difference being that sign there. And that difference in sign is the difference in these two. So the problem that I'm going to give you, if you square out all the terms, you'll see that they look very, very close, but there's a difference in the sign of the middle term, which means that you just get the same exact terms squared, but with the opposite sign in the middle. Because the numbers are going to get quite large if you keep doing a bunch of stuff with them. But if you just realize this fact, then you can just go, okay, I'm adding 1. When I put that in, then I'm going to get the same exact thing, but with a plus sign. So I would like you all to try this arc length problem. And then I would like you to try this surface area problem. All right, so I'm going to go ahead and stop recording.